Okay, so let's talk about electron configurations. So electron configurations are the next step that we take from the orbital maps. So when we look at the main overview of electron configurations, this is how it looks if you weren't using your electron configuration periodic table. You'd have to know that each of these dots hold 2 electrons. Each level needs to be completely filled before moving on to the next level, and that each level will fill with 1 electron per dot before moving on to fill with a secondary electron. Got to remember, as we've talked about before, the larger and farther out the electrons, the harder it is to hold, so they have increasing energy to hold them through. So 1s being the least energy, 4f being the most energy. So let's look at how we can fill an electron configuration using our orbital maps. It's a think process. So remember, s orbital holds 2 electrons, the p orbital holds 6 electrons, the d orbital will hold up to 10 electrons, and the f orbital will hold up to 14 electrons. Now, I've kind of made this very interesting kind of orbital map. And if you follow the arrows when they go through, it'll tell you how they will fill in what order. The trick, though, is if you're following the electron configuration table, that's how you do it. So it goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 5f, 6d. And yes, there should be 7. So I think it got cut off and I apologize. But this is how it fills if you just follow the arrows. Now, an easier way of using this is just using and memorizing the electron configuration periodic table, because it does the same thing without you having to memorize arrows and numbers. I honestly wish when I was in college that they had taught me this instead of the electron configuration table, because I understand it, it makes sense to me. This was always a struggle to understand. So there's that. So let's talk about how to use a periodic table or the electron configuration periodic table to complete an electron configuration. The steps are almost exactly like orbital map notation. So here is my electron configuration periodic table. The S is green, the P is yellow, the blue is F, the pink is D. Also, I have highlighted my full orbitals in this orangey color here. So using the electron configuration periodic table, or a periodic table, because remember, you're not allowed to use these on a test. You can memorize them. You've got to find your element on the periodic table, put your finger on it, list all full orbitals before the element, and then list the configuration under your finger. You can either do it 2 ways. You can do it just how they fill on the periodic table and out of quantum number order, and that is okay. Or you can do them in the quantum number order like you would do on orbital maps, and that is also acceptable. Okay, so let's conduct or complete the electron configuration of aluminum. So the first thing you're going to do is put your finger on aluminum. Aluminum's in the 3rd row, first element on the P block. So I'm putting my finger on it, or in the case of the computer, I put my little blue square on it. Now, the first thing you're going to do after that is just list all the full orbitals before the element. Remember, you're writing from left to right, top to bottom, row by row. So in my first row, my first full orbital is 1s2, and then I would write 1s2. In the second row, my first full orbital is 2s2. So I would write then 2s2. Moving along the second row, I have another full orbital. I have 2p6. So then I would write 2p6 after 2s2. In my third row, I have a full orbital before where aluminum is, and that would be 3s2. So then I would write 3s2. I have no more full orbitals before aluminum, so then I just go ahead and lift up my finger and write that configuration under my finger, which is 3p1. Now remember, if you are using a periodic table and not an electron configuration periodic table, you can remember that the end of each block, that's row 2 for the S block, row 12 for the D block, row 18 for the P block, and the end of the F block are always full orbitals. So all you will have to do is remember where your quantum numbers start and be able to count over how many columns you are to find that final how many electrons there are. Because remember, the D block has like 10 columns and each column adds another electron. The P block has 6 columns, and that first row, the boron family always has 1 electron in the P block. The carbon family always has 2 electrons in the P block. The nitrogen family always has 3 electrons in the P block, oxygen 4, fluorine 5, noble gases 6 in the P block, except for helium, which is 2 in the S block, so on and so forth. So let's do the electron configuration of iron. So the first thing you're going to do is find iron. It's in the 4th row, and you can put your finger on it. It's in the D block of the 4th row. Once you find it, you can put your finger on the periodic table, or you could still be using the electron configuration periodic table. You could go ahead and start listing your full orbitals. Again, left to right, top to bottom. So going along my first row, my first full orbital is 1s2, and then I would write 1s2. Then I would go to my second row. My next full orbital on my second row is 2s2, and I'd go ahead and write 2s2. Going along the second row, my next full orbital is 2p6. So then I would write 2p6, because remember, you only ever write full orbitals except for your final one, which may not be a full orbital. Going along my third row, I have a next full orbital is 3s2, so I would write 3s2. Moving along the third row, I get to 3p6, because that's my next full orbital. Moving along the fourth row, I get 4s2, and then I have no more full orbitals, so I can go ahead and write the configuration that represents iron as an unfold d orbital. It's 1, 2, 3, 4, 5, 6 columns into the D block, so I know it's going to be D6. The first row of the D block is 3, so I know it's going to be 3d6. So let's complete the electron configuration of iodine. Iodine is in row 5, so I put your finger on it. It's in the 5th column of the P block in row 5. So the first thing we have to do is, again, list all the full orbitals before the element. So going left to right, top to bottom, I have 1s2, and you write that down, followed by 2s2, and then I would write it down, followed by 2p6, and I would write it down, followed by 3s2, and you would write it down, followed by 3p6, which I would write down, followed by 4s2, and I would write it down, followed by 3d10, and I would write it down, followed by 4p6, and I would write it down, followed by 5s2, and I would write it down, followed by 4d10, and again, write it down. And I have no more full orbitals before my P block, so I would go ahead and go, I'm in the P block. P is the same as a row number, so I know it's 5p. I'm 5 columns in, it must be 5p5. And I would write 5p5 down. Let's do one more sample of an electron configuration. Let's do thallium. Thallium's in the sixth row, first P block of the sixth row. So again, we're going to find it, put our finger on it, I put my blue dot on it, and we're going to go along and list all the full orbitals. So we're going to go left to right, top to bottom, 1s2, followed by 2s2, followed by 2p6, followed by 3s2, followed by 3p6, followed by 4s2, followed by 3d10, followed by 4p6, followed by 5s2, followed by 4d10, followed by 5p6, followed by 6s2. Now let's not forget in the sixth row, right after lanthanum, we had to jump down to the F block because on that D block between D1 and D2, we go from lanthanum to hafnium. Lanthanum's number 57. Hafnium is 72. That means the F block literally fits between them in atomic numbers. That is why we jump. So please don't forget the jump, otherwise you're going to be missing 14 electrons. So we jump down, and because we're not ending in the F block, we just represent the last number of the F block, 4F14, and we write it down. Then we jump back up to the D block, finish the D block at 5D10, write that down, and then we're done. We have no more full orbitals. So then we realize we're in the P block, so that our quantum number is the same as our row number. So it's going to be 6P because our block is the same as the orbital. And then we count how many columns into the P block we are. We're one column. That is my superscript for the number of electrons. So it's 6P1. Okay, so this is how you do an electron configuration in full. Let's do some practice and try the electron configurations for magnesium, arsenic, zirconium, and radium. Okay, so let's talk about the answers. Magnesium is 1s2, 2s2, 2p6, 3s2. Arsenic is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3. Now, there are two potential ways of writing this. If you write them in this order, in the order in which they fill, it is correct. You could also write them in quantum level orders, which would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, and 4p3, and that would also be correct. So you might see them written two ways. Both are correct as long as you have all the orbitals organized in the same order. Zirconium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10. And again, remember, you could write that also in quantum number order. And then radium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 4p6, 6s2, 4f14, 5d10, 6p6, 7s2.